Hello everyone, welcome back. We'll continue our discussion with properties of soil. In this session, I'll discuss about grain size distribution, or it is also referred to as particle size distribution. We'll straight away go ahead. Here, I'll read out the points and then explain here. Soil in nature. Uh, It exists in different sizes. We already seen this sizes, shapes, and appearance. Here there are some photographs. The clay, which is amorphous in nature, the particle sizes are less than 0.002 mm. Silt is from 2 microns to 75 microns, right? And then sand is still a precise, and then gravel is still a precise. So depending upon these attributes, that is, attributes are sizes, shapes, and appearance, the soil at a site can be packed either densely or loosely. You know that when the particle sizes are like this, if it's in shape, and then if you want to put it in a container, a little shaking will help you in packing them in better manner. That's what it means actually. So while packing, what matters is the size and shape. Hence, it is important to determine the percentage of various sized soil particles in a soil mass. Means soil will be consisting of all these particles. It will not be separately this only or separately this only or only this. It's not like that. It will be a mixture of everything. So the process of identifying which part is what percent is called size distribution analysis. So it is important to determine the percentage of various sized soil particles in a soil mass. And the process of knowing that itself is known as distribution analysis or particle size analysis. For this purpose, a particle size distribution curve is plotted. Now how to plot and all, we'll see it in detail. Now the packing of soil and amount of voids present in soil mass influence the strength and stability of the soil mass. It appears that when you shake it up and then if you pack it tightly, obviously the strength of the soil will be more, and if it is loosely filled and then voids are more, then obviously you can expect the strength of the soil a bit less, right? We'll go into the details of all those things. Okay, here are some more pictures of a variety of different soils. You can see that these two are almost clays, and this is slightly the grains are visible. You can call it as silty, and this is a sand. This is also a sand, and here comes gravel, right? The sizes of which you know that it is sand is from 0.075 mm to 4.75 mm. If the particles are more than 4.75 mm or 5 mm, or so to say, to easy to note it down, half a centimeter, you might be having a feeling of size 1 centimeter. So if the particles are more than half a centimeter, that is 5 mm approximately, then the particles are known as grain size, gravel size particles. Okay. Anyway, now what is the use of knowing particle size distribution? There are a number of applications or uses. We'll see one by one. Particle size distribution is used for the soil classification. Of course, we have a full-fledged classification chapter in which we are going to use the results of particle size distribution. It is used to design the drainage filter. Even this is also given to you when we study about filters, right? Now, size distribution is used to select the fill material of embankment, earthen dams, road sub-base materials. So this particular part we'll discuss in the chapter named compaction. Now, how much it gets compacted, where the density will be maximum. That is what is the kind of analysis you will be trying to see that in a chapter named compaction. Then another application is it is used to estimate the performance of grouting, chemical injection, and dynamic compaction. So when you do all this, if the particle size distribution is very nice or well graded, then the grout will be better. Otherwise, it will be having lesser strength. Then there is a term which is known as effective size, which is a D10, which can be correlated with the hydraulic conductivity. Hydraulic conductivity is nothing but ability of the water to pass through, or ability of soil to allow the water to pass through. That is conductivity. Now it depends upon what is known as D10. We'll be seeing what exactly D10 in a short while now. And more important to coarse grained soils means this particular particle size distribution is of important uh, index property as far as coarse grained soil is concerned, because if it is a fine grained soils, and then if we are trying to talk about particle size distribution, there is not much of use is there for fine grained soils. Okay, so here it is, particle size distribution, how it is presented. It is a graph. It is presented in the form of a graph with percentage finer. You can see here percentage finer plotted along vertical axis or ordinate in normal scale. You can see here 5, 10, 20, 30, 40, 50, 60, 70. All these are almost equally spaced. Some of the numbers are missing here, but what you can observe, it is an error of plotting. Otherwise they have to be equally spaced. In the sense, it's a uniform scale. The scale is not varying depending upon the sizes or percentages, right, in normal scale. And particle diameter d along the horizontal axis abscissa in logarithmic scale. It gives an idea about size and gradation of the soil, means this graph gives. Now it is said that it is in logarithmic scale along horizontal axis. Now if you look at this distance is marked as 0.2 microns, and equal distance if you go, it should have been 0.4 microns. Equal distance if you go, it should have been 0.6 microns. If you go further, maybe 0.8, maybe 1 micron, but here it comes 4.75 mm. It is 20 mm, 40 mm. If you analyze in a reverse manner, if it is 40 mm, somewhere here it should have been 20 mm, somewhere here it should have been 10 mm, right? Here it should have been 1 mm, but this is 0.2 microns. What is micron? Right, 1 raised to 10 raised to minus 3, 1 into 10 raised to minus 3 meters. So 0.2 microns is too small. 2 microns, it is 0.002 mm. Look at that, 0.002 mm, whereas this is 40 mm. So the plotting cannot be done in a normal scale. It has to be logarithmic scale. Again, there will be one more slide which is devoted for this. I'll explain you. Here it jumps by 10, right? Every distance when you go up, it will be multiplied by 10, so that you can plot the range from 75 microns to 10 to 40 mm size, right? Okay, further we'll see. A soil sample is well graded. Please note the word well graded. Here I'll highlight also. The soil is called as well graded if it has a good distribution of all sized particles. Otherwise it is called poorly graded. Means here it should have smaller size particles as well as bigger size particles, still bigger size particles. All of them should be there, not only very small particles or medium sized particles or a bigger size particles continuously. It should be a good mix of all. then it is called as well graded, right? A soil sample is well graded if it has a good distribution of all sized particles, otherwise it is called poorly graded. Now, uniformly graded soil sample is a special category of poorly graded. Make a note of this again. Poorly graded. Uniformly graded is not well graded. It is poorly graded. What is uniformly graded? Sample in which all the soil particles have the same size. If you have particles of the same size, one particle is there of exactly same size particle once again, exactly same size particle almost once again. So like this, if it is having the same size particle, maybe small, maybe bigger, but all the particles are of the same size, unlike the earlier case of well graded where there are smaller particles, medium size, bigger, like it's a good mix of all. But here when it is said uniformly graded, it has got all the particles of the same size. Obviously this is not so good. That's why it is classified as poorly graded soil sample, where the particles have the same size. Well, okay, what is gap graded? Here there is a gap graded soil sample possesses different proportions of the same sized particles in increasing sizes. Intermediate size particles are missing, right? Of course we'll be seeing through the graph also. Here what happens is a particular size of particles are missing. Intermediate size particles are missing, means it is not a good mix, right? It has got some mix in which a particular size particles are completely absent. That's why it is called gap graded. Okay, for achieving good density, means if you want to pack the soil into a good dense soil mass, well graded soils are most suitable. Means well graded in the sense it's a good mix of all. Okay, here there is one big important note. Particle size distribution is obtained by sieve analysis for coarse grained soils. Okay, it is also obtained by sedimentation analysis for fine grained fractions. You know what is coarse grained and fine grained fractions. So for fine grained soils, sedimentation analysis is used for particle size distribution. And then what is the method used is known as hydrometer analysis, is a popular sedimentation analysis which is used for particle size distribution of fine grained soils. Okay. We'll be talking about now in length about sieve analysis or coarse grained particle size distribution. Now here there are sample graphs one can understand particle size distribution. The results of particle size analysis are presented in terms of particle size distribution curve. So this is particle size distribution curve. This curve represents the type and gradation of the soil. That is what is said in this paragraph. The same thing we'll see here. Now there is a curve named A, green one, right? The curve is spreading from this corner to that corner, almost an S-shaped curve, right, which is going from one corner to the other corner for full length. So it indicates that the different size particles are present all along. That's why it is called well graded soil. So the green line represents well graded soil. So it is a mixture of all size particles. Now if you take part B or curve B, now look at this. From this point, that is maybe around 5 mm, here it is some, let us say 100 microns, that is 0.1 mm. From 0.1 mm to 5 mm you got all the particles, 100%, all the soil particles are lying. You don't have particles which are having lesser than this size. In soil B you don't have particles which are having sizes more than this. So it is almost of the same size particles. So this is poorly graded and you can call it as almost uniformly graded soil. If you want to have perfectly uniform graded soil, then you should have a curve almost a vertical line like that, so that the range of particles in which they fall will be very small. Look at this size range. The size range is very small, but whole soil, all the soil is lying in only in this much of size range. So it is of course a poorly graded soil, but it can be classified as uniformly graded soil. So that is about poorly graded soil. Let me take off this. Okay, now let me tell about the third one, that is gap graded soil. Now you got a curve C. Now you can just see here there are two dotted lines already marked. There is a horizontal stretch of the curve from 75 microns to 4.75, indicating that there is no percentage of the soil which is present in this size range. Means the soil C, look at this curve, soil C is having all the particles either less than 75 microns, or it has got particles which are more than 4.75, and there is no particle is having from size range 75 microns to 4.75. That is a horizontal stretch of the curve, indicates that you don't have particle. So obviously there is a gap of this particular size range. That's why curve C is known as gap graded soil. C is gap graded soil. So to repeat it once again, if the curve is stretching from one corner to the other corner, it will be indicating well graded. If it is almost vertical or in very small width, if the curve is falling, then it is poorly graded or uniformly graded. And then if the curve is having any horizontal stretch in that, then it is a gap graded soil. So gap graded soil is also a poorly graded soil, right? The only well graded soil is a good mixture. The other two soils, both of them are poorly graded soils only. Even uniformly graded soil is a poorly graded soil. Okay, so here there is a typical graph on which we plot the particle size distribution curve, right? So here you can make out on the vertical axis where percentage finer is plotted is very uniform. So here you got 10, 20, 30, 40, 50, 60 and so on up to 100%. Means all your soil will be falling in this stretch, vertical stretch, and it is well spaced, uniformly spaced. But if you look at horizontal scale, please note this, it doesn't start with 0. This 0 is for vertical axis. Horizontally, it starts with 0.01. You can start with 0.1 also, you can start with 1 also, or you can start with 0.001 also, right? Let me write that also. It can be started with 0.001. We'll see what is the change. Okay, now when you got this particular point measured as 0.01, this dot will be 0.02. Please make a note, because this is 0.01, this is 0.02, this will be 0.03, 4, 5, 6, 7, 8, this will be 0.09. Please note that this is 0.09, you got 0.1. So from this to this 10 times it has jumped, right? If I had started with 0.001, this will be 0.002, this will be 0.009. In that case, this would have been 0.01. Hope the point is clear. If I start with 0.001, this point I'll call it as 0.01, this I'll call it as 0.1, this I'll be calling it as 1 next. But as they have taken, this is 0.01, this is 0.1 10 times, again 10 times, this will be 1, again 10 times, it will be 10, further it will be 100, and so on. So here if we concentrate 0.1, this will be 0.2, this will be 0.3, 0.4, 0.5, and so on. This will be 0.9, this will be 1, and this will be 2, this will be 3, this will be 4, this will be 4.75. This vertical dotted line is 4.75. This particular dotted line is what is the size? This size is 0.075. okay, 0.075 or 75 microns. So that is the last sieve size we have. Because of that, this particular blue line dot, last dot, right, on the sieve analysis, we got a minimum size is 75 microns or 0.075. Then you got this as 4.75. The soil which will be lying from this 75 microns to this 4.75 microns is known as sand. So that is what is written here, right? So this stretch of soil is sand. And then if you have got particles lesser than this, then we'll call it as silt up to 0.002. And then if you got particles which are greater than this size, then we'll call it as gravel. So on size distribution curve, these are the salient vertical axis that one has to show. These two dotted vertical lines are indicating the classification. So here it is sand from this to this, right? If you are able to see this particular stretch is sand stretch. Further it will be gravel. Further down here it will be silt, right? But when you conduct the sieve analysis, the minimum point we have is 0.075. This can go a little beyond this, up to 10 mm we can go, right? So sieve analysis points will be ranging from this to this range. And then if you have a sieve analysis or size distribution lesser than this, then it will be because of sedimentation analysis or hydrometer analysis. Okay, we'll read through. There are some points here. Okay, D10 or D30 or D60 are the important particle sizes. Okay, now how do you find D10? D10, look at this. Here there is a mention of D10, right? Here some size is there, D10 size. Now what is done is 10%. D10, in that 10 is 10%. You have to draw a horizontal line. Wherever this size distribution curve is cut, there you have to find the size. Whatever this size is there, that particular size is known as, okay, here whatever size is there, this particular size, I don't know what size is. Roughly I can tell if this is 0.1 and then if this is 0.2, I can say that this is 0.15. okay, 0.15. They have given here it is 0.14. So D10 is equal to 0.14 mm. Okay, now what is the meaning of this? We'll see it afterwards. How to find D10? I told you 10%. You have to go horizontally wherever it cuts the plotted curve. There you have to find the size. That will be giving you D10 value or D10 size. Now similarly, if you want to find out D30 size, look at this 30% line. I have drawn horizontal axis, horizontal line. It cuts the particle size distribution curve at this point. I'll go down and find out the size, and this size I'll tell you 0.1, this is 0.2, and this is 0.3. Let us say it is 0.11. okay, let me write here that it is 0.11, let us say mm. So D30 is equal to 0.11 I'm sorry, 0.21 it should have been. I'm sorry, I'll take it off. Let me write it. D30 is equal to point, because this is 0.2 already, because 0.1, 0.2, this is slightly more than 0.2, say maybe 0.21 mm. So it is in mm. Okay, so D30, how did I do? I drew a line at 30%, horizontal line. I searched for a point of intersection on size distribution curve, went down to find out the size. Here there is a size, and that is 0.21 mm. Exactly in the same line, for D60, you should draw 60% horizontal line. It cuts here, I go down and find out what is the size. There it is exactly 0.4, and this 0.4 is again in mm only. Okay. Okay, D60 is equal to 0.4 mm. Now I'll read out the whole thing. D30, D60 and D10 are the important particle sizes. Now how we are going to use these things, we'll see it later. D10 represents a size in mm such that 10% of the particles are finer than this size. That is the meaning of D10 size. Means D10 equal to 0.14 mm. Because it is a percentage finer, we have plotted on this. D10 equal to 0.14 mm indicates this 0.14 mm indicates 10% of the soil is finer than this size of 0.14 mm. 90% of the particles are greater than the size 0.14 mm. You can generalize now. D30 equal to 0.21 mm indicates 30% of the soil is lesser than the size 0.21 mm. Lesser than 0.2 mm, 0.21 mm, or 70% of the soil is greater than 0.21 mm. Similarly, again, D60 equal to 0.4 mm indicates 60% of the soil is less than the size 0.4 mm. D60. So 40% of the soil is greater than 0.4 mm. That is the meaning of D60, D30, D10. Okay. The same thing is written here. D30 and D60 represent sizes in mm such that 30% and 60% of the particles respectively are finer than this size obtained on the particle size distribution curve. Okay, now terminologies will define in the next slide, but in this whole slide is devoted to understand what is meant by D10, D30, D60. One more final comment I'll give. D30 is such a size, here it is 0.21 mm, such a size that 30% of the soil is lesser than this size. That is the meaning of D10, D30, D60 and whatever you want to call. Now D10 is specially named as effective size of the soil. Whatever soil we have tested, for that if you want to find effective size or effective diameter, what you should find out is D10 is what size. So here it is 0.14 mm is the effective size of the given soil sample. Okay, we'll go further. Here this curve already we have seen, but little more details will be watching here. This particular shading is done for the soil which is having lesser than 2 microns, indicating that this is clay. Now This blue gradation of color is done for 2 microns to 75 microns. Means in this size range, the silt particles are lying. 75 microns to 4.75, in this size range we have sand, and the particles which are greater than 4.75 are called gravel. So if a soil is a good mixture of everything, as seen by a green line over here, it has particles of clay, particles of silt, particles of sand, and also some particles of gravel also. It is a good mixture of everything, that's why it is well graded. I'll come directly to C, the curve C, which has got horizontal stretch over here. I explained you earlier that the sand particles are missing. There is no percentage contribution for this, right? So that's why there is a gap of sand. Only you got silt and clay and gravel. There is no sand present in soil C. That's why it is called gap graded soil, right? And then the B is preferably uniformly graded, because you can just see that most of the soil particles are in the range of 75 microns to 4.75. That is to say, all are sand particles. Hardly there is any contribution of gravel, no silt, no clay particles. So to say, the soil B has got almost uniform soil particles. So it is a uniformly graded. So both B and C will be classified as poorly graded soil, particularly B, which is having the particles of the same size, is referred to as uniformly graded soil also. Okay. So the terminology that we are going to define with the D10, 60 and 30 are these two, that is coefficient of curvature CC and coefficient of uniformity CU. Uniformity coefficient or coefficient of uniformity is a measure of a range of particle sizes, particles present in the soil. Means what is the size range of the particles? It tells about that, right? So it is given by D60 divided by D10. It is a ratio. So coefficient of uniformity or uniformity coefficient is a ratio of D60 to D10. More the value of D60 by D10, it will be having more variety of sizes. If it is coming to unity, if it is nearer to 1, Cu is nearer to 1, then it will be having more of the same size particles. That is the meaning of coefficient of uniformity. I repeat that sentence. If Cu is nearer to 1 or almost 1, then it is poorly graded, or it is having particles of the same size range. And then if you have a value more than 4, more than 6, like that, then it will be having a good mixture of all size particles. Okay, there is one more term, coefficient of curvature. This represents the shape of the particle size distribution curve and is given by Cc equal to D30 square. Look at the way, D30, whatever size is there, it is squared up, divided by D60 and D10. So this coefficient gives you coefficient of curvature, the shape of the curve, right? Now here the values for different soils are given here. For well graded sand, please make a note of this, it is sand we are calling, not just soil, and it is well graded. If you want to have well graded sand, the Cc should be between 1 and 3 and Cu should be greater than 6. So ranges are given, Cu should be greater than 6, Cc should be between 1 and 3. For what? For well graded sand. Now similarly, for well graded gravel, the Cc should be between 1 and 3 and Cu should be greater than 4. Cu should be greater than 4. Cc should be between 1 and 3. Right? Now any one of these conditions, that is Cu value is given, Cc value is given, if any one of these two conditions, not both, not necessarily both, right?
is not satisfying the condition, then they are not well graded. That is said here. Even if either of the two conditions is not satisfied, any one of the conditions is not satisfied, then the sample is poorly graded. It cannot be well graded. Okay. Now, how exactly the grain size distribution analysis is done? Now, the methodology is mentioned in IS 2720 part 4 1975, gives the whole procedure. Here IS sieves, a set of IS sieves are arranged in order, with one having larger aperture at the top and that smallest at the bottom. Obvious, right? They have to be arranged. A lid at the top and a receiver at the bottom complete the assembly. Means there will be a top cover, and then below the sieve there is a receiver here, right? All of them are arranged in an assembly. A known weight of representative soil sample of say 1000 grams is placed on the top sieve. The assembly is vibrated on a sieve shaker. This is in a mechanical sieve shaker, and it has to be sieved for 10 minutes. You need not do it manually, so you have to do it in sieve shaker. Depending upon the particle size, the soil is collected in different sieves. Weight of soil in each of the sieves is measured. So when it is sieved, obviously all that soil passes through depending upon its size, and some part may end up in receiver also. Now you have to take the mass of each of the soil sample that is there in each sieve, and then with that what to do we'll see in the next slide. Okay, what are the IS sieve sizes? So these are IS sieve numbers. It starts with 4.75, 2.36, 1.18, then it is 600, 425, 300, 212, 150, and last one is 75. So in sieve analysis, the last sieve that is over here is 75 microns, or 75 sieve size. Now this is sieve number. What is the aperture size or opening size of the sieve? That is given here. Sieve size in the sense not this size, but openings that are there inside the sieve, that size. It is 4.75 mm, largest opening that is there over here on the top, right? Then you got 2.36, approximately if you observe it is half. 2.36, again half, it is 1.18 mm, right? If you hold it as 1.2, again half, 0.6 mm, right? This is 3/4, approximately 425 microns or 0.425 mm, and here there is half, that is 0.3 mm. Again there is half here, 0.15. In between you have got 0.212, then half of 0.15 is 0.075 mm. So you can, I think, able to judge what are the size ranges. The last one at the bottom is 0.075 mm or 75 microns. The upper one is 4.75 mm, and the table of calculation consists of these columns. We'll see with one numerical value. Okay, here weight of soil on each of the sieves. After shaking, you'll be getting soils which will be there on the each sieve, and that is collected and mass is taken. So it is, let us say it is given 60, 110, 150, 170 and so on, and even in the receiver also we have got some sample 50 grams. Means the 50 grams soil is passing through 75 microns, that way, right? Total is 100 grams. Now for example, if I take any of these like 150 grams, 150 grams is passing through 2.36, but it is not passing through 1.18. So this 150 is in between 2.36 and 1.18. Likewise all these masses are. Now, cumulative weight, in the sense, see here, the particles which are above 4.75 are 60 grams. 60 grams. This 110 is passing through 4.75 but staying above 2.36. Now if I sieve the whole soil with only 2.36, how much would have stayed on the top? It would have been 110 plus 60, that is 170. So it is a cumulative weight retained above 2.36 will be sum of these two, 170. Similarly, if I take the whole soil and sieve it through 1.18, how much would be the sand which will be above 1.18? It will be this 170 plus 150, that will be 320. So likewise, if you go on adding these numbers, you'll be getting this total, and it has to be up to this point, it will be 1000, because that is the total amount of soil taken, 1000 grams. So cumulative weight retained. Now what is the percentage of weight retained? If I want to calculate 60, I'll have to divide by 1000 multiplied by 100, so to say divide by just 10. So if I just go on dividing by 10, I'll be getting 6, 17 and so on. What is this? This is cumulative weight or mass retained above a particular size. Means 6%. 6%, total 6% of the soil is above 4.75. If I take another case, 60% of the soil is coarser or thicker or greater in size than 425 microns. Is it making sense? Just look at that. 425 microns and 60 grams. This is a cumulative. In the sense, 60, not 60 grams, 60%. 60% of the soil is greater in size than 425 microns. Then here 95% of the soil is greater than 75 microns. Okay. Now if it is retained, if it is greater, if I want to find percentage of finer, then I'll have to simply subtract these numbers from 100. So it is 94. Now what is that 94? It simply indicates that 94% of the soil is finer in the sense smaller in size than this 4.75. Similarly, if I take this 1.18 mm and 68%, what I can describe it as is 68% of the soil is smaller than 68% of the soil is smaller than 1.18. So with respect to this sizes or these sizes, I have percentage finers. Percentage of the soil finer in the sense smaller in size than those sizes. Now further, this data is plotted in a graph. I have told you that the size range is plotted in terms of log scale, and then percentage finer or percentage passing, this part is plotted uniformly. Now you can see, check here, 10, 20, 30, 40, 50 and so on up to 100. Uniform distribution of the scaling is there, whereas here it started with 0.001, 10 times is 0.01, 10 times is 0.1, 10 times is 1, 10 times is 10, 10 times is 100. So here you got 0.0075. So where is 0.0075? Obviously here 0.01, 2, 3. So this particular point would be the beginning point, 0.075, and then I have 4.75. Obviously my last point on this graph would be this green dot over here, because it is 1 and this is 10. So you got that point, that is 4.75. All my points will be from this to this. These are extra point, maybe with other data they have plotted. This is also a data which is beyond our table. Our table is ranging from this point to this point. That's all. Okay. Now when you have the graph drawn, a care has to be taken here. The graph has to be drawn such that it has to pass through all these particles, right? All these, I mean not particles, points, all these points. You cannot draw a smooth curve, right, which is not passing through the points, because it is exactly the same points. Because of that, you have to run a graph, run a plot passing through each and every point that is plotted, and then find out d10, that is you go to 10%, draw a horizontal to cut the curve, come down, search for the size. This size will be recorded as d10. Similarly 30%, I go here, then I go down here, I'll have to find out what is d30, the size, and 60, again I'll have to go here and then find out the size here. So d60 is so much. Now after finding out the sizes of d10, d30, d60, I will have to work out cu and cc, and depending upon whether it is a sand or a gravel, I can name it whether it is well graded or poorly graded. Now how to identify whether it is a sand or a gravel? That will be part of classification. I want to emphasize this particular point. From these, from the grain size distribution curve, you may not be directly able to or say that it is a sand or a gravel just by looking at the values of Cu and Cc. I repeat this sentence. Just by looking at the values of Cu and Cc, you will not be able to judge whether it is a sand or a gravel. But if it is predefined that it is a sand, and if they say Cc is so much and Cu is so much, then you can comment on gradation, whether it is well graded or poorly graded. Right? If it is not predefined, then you cannot comment. Make a note of this and take care. Now how to identify whether it is a sand or a gravel? That will be part of classification. We'll discuss that in detail afterwards. Okay, with this I think I can conclude. Thank you.